All right. Hey, welcome everybody. I'm Nick. I've wanted to give this talk for a really long time. This is a session about parsing little languages in C#. So you might call them domain-specific languages maybe, but really we're talking about any kind of little language that you could embed into your own applications. And I really want, by the end of this talk, for you to feel like you not only could, but that you might actually consider giving this sort of thing a try in real-world projects. So unfortunately, if you read too quickly and you got parsing C# and you're expecting a Roslyn talk, the door is still open. But I can't really think of anything any programming technique that I've learned that has had a bigger impact on the kind of software that I could consider writing than this. So even if you were expecting Roslyn, you still probably might get something out of this hour. So let's get stuck in. Let's pay a clicker. So Eric Meyer, who I think you'd probably recognize for his work in C# on the link language features particularly, he once quipped that dependency injection is for programmers who don't know maths. He's got a good sense of humor, I think. But so sometime back in 2008, 2009, I was sitting at my desk. Hey, my boss is really interested in this dependency injection stuff. We're just down in the cafe. Could you come down and maybe answer a few questions for us? I show up at a cafe. Eric Meyer. Great. So it's the first time I've publicly admitted this, but I feel some kind of responsibility, as though I might have failed to really get the beauty and joy of composition using IOC and dependency injection across to him. But at the same time, I came to write this talk, and there's those words again. And I thought, yeah, well, I've got an hour to deliver the talk, and I won't get all the content into an hour, surely, so we'll save 10 minutes for questions at the end. And then I need at least 30 slides. So how long have I got to present each slide? And if we Alt-Tab across, I thought, well, I don't know maths, obviously, but I know a few things about computers, so could I come up with a scheme to get a computer to solve this problem for me? And so here we go. It's something like 1 hour minus 10 minutes for questions. Oh, hang on. Oh, and we need some parens because I know enough maths about that. 1 hour minus 10 minutes. And how many? 30 slides. OK, so we've got 1 minute and 40 seconds for each slide. I can just about squeeze it into that. If we've got 10 minutes for questions at the end, and I'll probably need 30 seconds for every question, 10 minutes divided by 30 seconds per question. OK, I probably could have worked that out in my head. Still, in lots of domains, it's really nice to be able to express a problem in a natural way. And as programmers, we really intuitively know that languages are kind of the optimal vehicle for this. Just switch back across, sorry. It's a little bit like if you remember when you first encountered a database, the way that you queried it was probably with something like a visual query designer where you dragged on tables and joined them up. And now that's a good experience if you have no knowledge of databases and you need to get data out. But if you spend all day every day dealing with an application the way that the people who use the software that all of us write do, then you know that often being able to express a query in SQL is a must. There's no way you could imagine being a programmer and working with a query designer day in, day out. And it's very much the same for lots of our users as well. But historically, at least with the teams I've worked with, we're really, really hesitant to embark on adding languages into our projects. I'm not sure if it's because we're afraid that there's some specific knowledge that means the next programmer down the line won't be able to maintain it. I kind of suspect that when we first encounter languages, it's in an academic setting, and there's a huge and really interesting field to explore there. And all of the really sophisticated techniques that you might use if you're implementing something like a programming language day to day, it obscures how easy it is to use very simple techniques to approach these problems in languages like C#, doing things like writing business apps. So once I discovered what I want to show to you today, it was like having for loops in the toolbox or learning object-oriented programming. I mean, there was just a whole host of ways of approaching software and ways of tackling problems that all of a sudden became open to me. Like when I started working on Octopus Deploy, right back with Paul Stovell, there was a feature where you could substitute variables into your configuration files, but you couldn't generate configuration files or conditionally construct those. And so a little language was born in there for conditionally, for flow control and looping that let you do a lot more. And I'm sure some of you probably have used those sorts of techniques today, and I can't imagine Octopus without it myself. I worked with a hospital who had an admissions system for expectant mothers coming in to give birth, and there was this legislated list of questions that had to be asked in a particular way, and the questions would change every year that they had to answer and deliver back to the health department. Unfortunately, because this was implemented as a large web forms application, it took something like 18 months to go and grind through that list of questions and turn it into an app that you could actually enter data into. So there's obviously a problem there. And once we came back to taking the questions as they were delivered and using a small language to conditionally show or hide those questions based on previous answers, we took that whole process down from 18 months to a matter of hours. Unfortunately, we built it in Silverlight, and literally 1 month after we finished the project, the hospital, I believe, standardized on iPads, and that was the end of that. So you win some, you lose some. I also, when I hit the problem of getting better diagnostics out of .NET apps, spotted a chance for using little languages in logging, which you might have encountered in Serilog. And Serilog's got a filtering language built into it too, which is something that's also indispensable in this kind of software. But these are all things that I wouldn't have imagined attempting to write had I not kind of ripped the bandage off and learned how to deal with parsing text. So if we go back and have a look at the little duration calculator that we ran earlier, most of you can probably see the essence of the problem just straight off the bat like that. When we want to evaluate something like 1 hour minus 10 minutes divided by 30, we kind of intuitively know that the shape of the problem is a tree. And irrespective of the programming language, it's pretty normal to represent these sorts of structures in trees. For example, we might have an abstract hierarchy where there's expression, duration value, numeric value, and some kind of binary expression node that can have a left and a right expression and an operator. Most of us are fairly comfortable with working with trees because we do that every day. So why is it that, and of course, here's I think, just case in point that the code to evaluate this particular language once you have kind of gotten your problem into the shape of a tree is very short. You could sweat away over switch statements and recursion in an afternoon and be able to compute a result. So everyone's fairly comfortable, I guess, with recursion. Everyone will be quite happy with a tree and writing a procedure to go through and evaluate this, but comfortable with writing a parser to get to the tree. This was my predicament as well. So we've got the input language, and it's a string of characters. And we want to somehow just bunch those up in just the right way that once we've processed those and walked through them, we'll have a tree that we can then go and use regular programming to evaluate. The nice thing is that this is just programming. But unfortunately, the techniques are kind of distinctive to this space. So we've all seen how regular expressions can be used to chop up a string into components that are all linear. But if you want to produce a tree from that output, you have to use a parser. There's no recursion in regular expressions, and there's no stack, I guess. And trying to use one where you need the other is obviously a world of pain. So what is a parser? So deep, no. A parser is just a function that takes a string as input, essentially, and gives you a value as an output. That's kind of everything and nothing about the problem, right? To make useful parsers that can manage sophisticated languages, that we have to be a little bit more prescriptive. And although our parser functions are going to have very much that shape of take a string as an input, produce a result as an output, I want to introduce you to two little structs that will appear through the code that we're going to write. Input wraps the source string, and it gives you a position into that string. So where you're up to as far as having consumed the characters to produce that value. And a result tells you whether you successfully parsed a value or not. And in both cases, either what was the remainder after parsing the value, or where did you hit the error. And there's not really a way to kind of just continue. These are both immutable, so you don't kind of go around and push the position of an input along. To get a new input, you have to consume a character from an existing input, and then using next char, and that will give you a value and the remainder. So how's this going to work? This is a very simple parsing problem. It's not the most simple, but let's take natural numbers, for example. The algorithm for parsing a natural number, if you think about working through this one character at a time, is that we see a 1, if we're parsing 123, and then we move on, and is the next character also a number? And if it is, we'll multiply that first one that we saw by 10 to shift it up a place, and then tack on the next thing that we saw, which is that 2. As we keep working through that string, each time we find another character, we'll multiply whatever we've got by 10, and then tack that last one on. So maths. I can get that far. Now, it's a little bit noisy once you include input and result into the equation, but here's a reasonably defensible parser for working through an input and parsing off a natural number and giving back the remainder, whatever input has not yet been parsed. And it's not code that I like. It's fairly ugly, but it's code that anyone given some time to think about the problem could obviously put together. So parsers being functions, we can write functions to do all kinds of parsing tasks, and we don't necessarily have to write an A function if we just want to parse the letter A, or a B function to parse the letter B. The char function here is a parameterized parser where you can tell it which character you want to match. So it might be an A, B, C, and then the result of that char function will be the character, if that was the first thing that was seen in the input, or it might be an empty result if that character didn't appear. So if you've got a parser for parsing natural numbers, which there wasn't any magic in, no one saw any magic, or char unicode info.get digit value is probably magic. I don't know how that works. There's got to be some kind of shifting involved in that. But if you can parse natural numbers and you can parse characters, you can imagine writing another parser for fractional parts, which is very much like natural, except that instead of multiplying by 10 each time we move up a place, every time we move off into those fractional digits, which is that way for you, then we would divide the next number by 10 to add it on. So given 3 fairly simple parsers, we can then go and write another function And it's also got that same signature where we're taking an input and producing a result. And this one's going to parse decimal numbers. In this case, we apply the natural parser to get the whole part. If we failed, then we bail out. If we can then parse a dot, we move on. We don't really do anything with that value. And then we apply the fraction parser. And if the fraction parser has a value, then we're able to add the whole and fractional parts. And there we go, we have a double. What do you think of this code? I hate it. I can't imagine trying to maintain any kind of giant code base that's written in that style. That's probably why you wouldn't imagine being able to scale from some sort of simple little parser that looks at numbers up to being able to really parse a whole programming language with these techniques. But let's tear it all down, reset, and start again. So because parsers are functions, there are some tools in C# for dealing with functions that we can apply to make working with parsers a lot easier and much more pleasant. The term might kind of be higher order functions, but we don't want to get too technical, right? Not getting into maths or anything like that either. This parser, so to declare a parser, we first need a delegate type. To work with parsers as functions, we need a delegate type. The parser of T, delegate, is just capturing that signature where we've got an input and we're returning a result with a value. Once we have that delegate type, though, we can start to write other functions that will process parsers into new parsers. And many is a really neat little example here where we have a parser for an item, and you can imagine that being something that turns smileys into their Unicode equivalents. And then we have this function many, and if we call many with the smiley parser passed in, we get a new parser that can give us lists of smileys. And that's a really powerful concept. But to fit that model, of course, we then have to go back and revise things like char. And char now, in this version of the code, is a function that doesn't actually do the parsing, but will take the input and, that will take the character and then close over that and give us a new parser that will match that character. So back to the problem of parsing decimal numbers. The repeated code that we saw in there was that apply one parser, check whether the result had a value. If it didn't, return an empty value with a particular remainder. And if it did, move on to the next part. So given that we can work on parsers this way, this function then is a sequencing operator that will take the parser, which is the first thing that we're going to try to match, and then return a new parser that, and the second parser that we're going to try and match, and then return a new parser that's going to apply the first and then apply the second. And inside the body of that little lambda there, you can see the same pattern that repeated 3 times in parsing decimal. The return function is a helper that we'll see used in the next little slide, and it just is a simple parser that always returns a value regardless of the input and doesn't consume anything. But with these 2 ingredients, we can take a much better swing at building a maintainable parser out of those component parsers that we've already constructed. So you can see here, the nice thing about this is as well that it reads like English or reads like the grammar that describes the language. So to parse a double, we parse a natural typo, didn't spot that. And then we take that whole part that was parsed and we construct a char parser. And if that matches, then we take the dot and ignore it, and then we apply the fractional part, and then if those have all succeeded, we return the whole number plus the fraction. So this technique is really interesting, not just because it's succinct, but also because it's kind of fractal. You can take a simple parser and build a more complex parser, and with just these few building blocks, you can build parsers for really arbitrarily complex languages that all have the same kind of structure at each level. And this technique's been known for quite a long time. It's, I think, at least known since the 60s. But quite a number of people have worked on it, and 2 computer science researchers cemented its popularity, I think, with an article in 1996 about it. And one of those, of course, happens to be Eric Meyer. And so given that Dr. Meyer's had something to do with this, it's probably no surprise at all that the C# language has some really good facilities for doing this kind of functional programming and this kind of combination of parsing bigger things from small things. So with the C# query comprehensions, we can create a function called selectMany, which fits into that from in structure. And it behaves very much like then. And so now we not only have a composable way of building parsers, but we have a little domain-specific language that lets us express things like from, well, we take the whole, or we take the dot, and then we take the fraction. And all of the features of link, like let and where, go in there to give us a really succinct and powerful language for writing parsers. So I think that's really awesome. Then, of course, and return are not the only games in town. Once you've got this capability, there are all sorts of things that you can cook up to tackle different kinds of syntactic structures. Like if you are parsing a list, then you can write a combinator called many, and it will take an item parser. Or many delimited by will take those items and look for another parser in between them, like the comma that you'd find between items in a JavaScript list, for example. So the even better news is that you don't have to go and write all of this yourself. If you were really itching, though, to get back to the hotel room and crack open an IDE and start writing parsers, that's totally cool, and I don't want to deter you. But there are some libraries already available in C# and .NET for doing this. The one that we're going to look at through some further examples is called Superpower. It's the second attempt that I've made at trying to write a parser combinator library for C#. And this one comes with, of course, a set of combinators like then and many and or. And it also comes with a very large sort of library of pre-built parsers like the numeric parsers and parsers for decimal syntax and those kinds of things. So it can take a lot of that nitty-gritty out of trying to build a parser for a new language. It's still good to know, though, how all of those little individual unit parsers are working, because the nice thing about working with parser combinators is they still are just code and they run like programs. And if you can write code, you can debug code, you can try writing a parser for a particular kind of language, and then you can debug your way through that, which is a big difference from if you were trying to express something in EBNF grammar and use the language workbench. And yeah, of course, there's a whole lot more to it too that we're going to have a look at. So the first parser we'll look at that's built with Superpower is this one called Magnitude. And if you recall, we had a little domain-specific language for computing durations. And the unique thing, I think, about that language is just the duration syntax. I say unique. It appears in a few places, but it's not something you typically find in day-to-day programming languages. And this parser is called Magnitude because it's what we're going to use to parse that little trailing piece of text after the number to decide how big that duration is. It's not called duration because we've already got a library parser for parsing numbers. Okay, so when we want to parse 10 minutes, we just need to find the minutes bit, and then we'll multiply that by 10 to get 10 minutes. Written here, it's quite verbose, and being a program, it could be refactored. I haven't done that just because I think the structure is nice and clear. And if you read your way through it, you can see that we'll try to match a character D, and if that matches, the value is 1 day. Or we'll try to match the character H, and that'll be the value of an hour. Things get a little bit interesting around M and MS. Now, if we were to put minutes ahead, just following that sequence that we have been working through, and we encountered an M in the input, then that M parser would succeed, and we'd never look to see whether there's a trailing S to decide whether it's minutes or milliseconds. This is kind of one of the consequences of writing a parser like a dumb program. But it's also one of the benefits, because the way that you resolve these sorts of ambiguities is really straightforward if you're used to sequencing programs. It's like, well, of course, we'll just try the MS bit first before we try and match the M. And that way, if we could chomp up that whole ms, then we don't need to try the m. And if we fail, we'll just backtrack and the m parser will kick in. Try stuck in the middle there. I should say character equal to d or character equal to h is exactly the char parser that we saw a few minutes ago. It's just that it's organized alongside a whole lot of other kinds of char parsers like letter and digit and those sorts of things under that character class. If we parse our way through something with Superpower and we fail partway through the input, then that will generally completely fail the whole parsing job, because reporting errors really relies on giving back information that's really specific. So if we parse our way through some input and we fail, that's it, or doesn't actually try to pick up another parser and try the next one in the sequence. And so the try combinator is in there that causes this one to backtrack, because we do want to continue if we partially matched ms. I didn't say this was all going to be super easy, only that it's code and that it's understandable from that perspective of working through an algorithm rather than trying to understand a grammar. Once we have magnitude, we can start to parse durations. And in this instance, we use the decimal double parser. And it matches the numeric part. And the name is awful, but the name comes about because the library of parsers we're using has parsers that simply match a span of text with names like decimal. And then they have, there's a lot of variants for some of them for efficiently turning that span of text into a particular .NET type. There is decimal, there's decimal double, there's also decimal. Token just tells us that it's OK to surround that with white space, so it's another parser that goes and tries to chomp through as much white space as it finds before applying the parser that it wraps. And then we see then, as we did in the earlier one, where we try and apply magnitude, and if we succeed on both, then we can pop back out a duration, that captures that time span that the expression or that the token has encoded. So one of the strong benefits of parsers being code and parsers being the same at all levels is that you don't just test the overall grammar for the whole programming language or domain-specific language that you're building. Here, we've got a test that's just for parsing durations, and we can use a little helper function called test parser. Oh, sorry, try parse all, which will just go and apply that parser we've passed through, which is the one we're testing, give it some input, and then we can assert different things about what we got out of that. And that works whether we're talking about parsing a duration, parsing some kind of binary operation, or parsing the entire expression. And these are also highly amenable to data-driven testing, where we take a whole list of possible inputs and we loop through and put them through a function like this and test them against their list of possible outputs. So to counter anyone who tells you that you shouldn't write parsers in your biz apps or whatever it is that you're doing for real, parsers are so much more regular and so much more testable and modular than anything like a web form, that they're really much more controllable when you're doing things like testing and changing them. I mean, I can imagine there's some really colossal web forms out there that no one would think twice about writing, but which are certainly not anywhere near as testable as a parser. I can also imagine somebody right now sitting behind their cubicle monitor in some colossal MVC form, like entering durations and checking them with checkboxes and grouping them up and applying operators. Like, yeah, the alternative of writing things without a parser is often a lot messier than if you were going to use these techniques. So, given that we can parse durations, and parsing operators is pretty simple. Here I have factored things a bit. The op function takes the symbol, and then the parser that represents takes the symbol and then the enum member that represents the operator. And so we have plus gives us operator add, and minus gives us subtract, and so on. And so again, it's just programming, so we can get those four for the price of kind of 1.5. we won't do too many more slides of just kind of like piles of parsing code, but this one is the meat of the duration language that we've been looking at. We probably need to spend a little bit of time looking closely at it, because this is, I think, the one that captures the difference between the really linear parsing that we've been doing and being able to kind of recursively construct those expressions that we're going to represent as trees. So literal is pretty simple. It's the lowest level kind of node in the language. Pardon me. So a literal is either a duration or a number. And we see because durations start with numbers, we have to backtrack potentially using try so that we don't fail, having seen just the numeric part. Factor has an interesting name, and the names are maybe a little off-putting, but factor is the part of this language where it might be what you would find on the left or right-hand side of a multiplication or a division. Because we're dealing with operator precedence, the things that are kind of bound more tightly are up towards the top of these little parsers, and the things that are bound more loosely are down the bottom. So a factor, we have a left paren, and then we recursively parse an expression, and then a right paren. And so this is how you apply the language to, this is how you apply the parser to something like our 1 hour minus 10 minutes in brackets, so that that's grouped up and can be multiplied by another value. And if otherwise, the literal is the kind of tightest unit. And if we go up a little bit further on, we've got term, which is something that you might add to something else. And it uses a helper function called chain, because parsing left associative expression grammars like this one is a really common task. And so there's lots of little library helpers to make that easier. And chain will just take the parser for the value, and then whatever it will take the operator and the operands and use that to construct some kind of binary expression node. Term and expression are really very similar in that one is applying multiply or divide, the other one is applying add or subtract. This could be a little bit horrific still to look at, and I think this is one of the other points that's important to realize when you set out to build a parser for a language that you've concocted for your own purposes. When you set out to write a language to solve a problem, it's very rare that the language is the interesting thing. It's usually the problem that's the interesting thing. The model of your domain is where everything that's unique to your language is going to be. So I can write 1+1 in JavaScript or SQL, or a SQL query, or probably in XSLT if I encode it right. And that looks the same in all of those syntaxes, but the semantics of actually executing that is very different. So if you put your X-ray goggles on, you can see that there's a whole lot of commonality between most of the languages that we as programmers would design to solve problems. You might have expressions. There's data types like strings and lists and numbers, and no one goes out to invent their own decimal syntax. And if you've got to encode strings, then you're probably going to adopt something like JavaScript strings or SQL strings. And so because of this, there are only really a few sort of skeletons for most of the kinds of languages that you might write. And I can't sit and write the correct code for a parser like that expression one we were just looking at on the first pop off the top of my head. However, I don't need to, because I open up any example expression parser written with Superpower or otherwise, and that structure is kind of there and documented, and somebody else has solved that problem before. So you don't think you really have to go back and really understand every single approach to every parsing problem to be able to be effective with this stuff. Take a little bit of the pain sometimes in things like constructing an expression tree, and then adding in those elements like different kinds of values and different kinds of operations is where your language will become interesting. So before we can run the parser that we have written for expressions, it's important to check that the string that we're trying to parse is actually the complete input. So you can see there's one little helper there called source, which takes the expression, uses a combinator called @end just to assert that the result of that parse has consumed everything. And then try parse is just a little wrapper that goes and constructs the source object and calls the parser and returns the result out. But so that all adds up to give us what we've been looking at a few minutes ago. So if we have a look at how it behaves, you see it does work, I think. Oh, yes. I should probably, again, we probably need some brackets there before that would make any sense. So that red error there is one that you get when the expression syntactically makes sense, but that's in the evaluator. It's said, well, you've got a time value and you're trying to subtract a number. But there are other kinds of mistakes that we can make when we're working with little languages. And most of the time, because this is built with a framework that has a whole lot of code for dealing with producing good error messages from broken parsers, you'll get a message that makes some sense. There might not be enough input. There might be something like, if I channel my German heritage, 45 Tag, there we go, an unexpected T, or something that just doesn't make any sense at all. But this is where the difference between different approaches to parsing start to really make themselves felt, because an error message like unexpected 1, when you're looking at an input like 1010, makes sense to a developer. Like, if that was an exception message, and I knew that I was parsing some kind of expression, that would be perfectly fine with going and tracking that down. However, little languages will crop up that make it easier to write programs, but they're mostly for the benefit of users. So if we were going to actually ship something like this in a replacement for a giant web form, hang on, I can't F5 that. I might want it to look a little bit more like this. Okay, so here we have our old input, so 10 plus 45 T. Okay, so this is telling me I've got an invalid duration. I've got an unexpected T. If I have 10, 10, I get an error that's an unexpected number 10. So these are starting to approach the kinds of error messages that you could show to a human user. And maybe this could be another reason for the trepidation that people feel when they're going to add a parser into a real-world project, because producing good error messages for users that make sense and don't result in emails and support calls is a little bit trickier. But I think it's important to understand where that line's drawn, so that if you are in one of the boats or the other, whether you're writing a parser that's going to be used by developers, probably yourself or your own team, versus if you're going to have third-party users, you're probably better off setting off down the right path from the very beginning. And so to produce better error messages like these ones, we need to go just a little bit further. So the technique that produces messages like unexpected duration, expected operator, is made much easier by an approach called token-driven parsing. And I think that the techniques, sorry, I skipped ahead, but if you take the character stream we've been parsing, like a simple little operator like that, we're looking at everything a character at a time. And that's very useful for our understanding of that task, because the parser makes makes a simple algorithm working through those characters, and everything's sort of at the same at every level. But to a user, there's a lot of higher order structure in there. Users are typically going to be thinking of those as whole tokens, like 10M is a duration. I'm not really looking at a 1, a 0, and M when I'm a user. And so the job of a tokenizer, which is a kind of just a glorified preprocessor for for input like this is to go through and group up those tokens and discard all of that trivia that you don't need in order to successfully parse the thing. By doing that, we can attach a whole lot of information to those in the process. And it's not the same as just doing some parsing first, because tokenization is still much more like what you would do with string.split or regular expressions. It's a simple process, and it's not particularly intelligent. It doesn't tell you what the role of one of those structures is. It will just tell you what they are. So a left paren is a left paren. The divide operator might be a divide operator, or it could be the start of a comment, so it's just a slash. And when we tag those tokens that we found in the token stream with their kind, we just come along and chomp them up exactly the same way as we did the other characters in our first version. So to convert the parser we've already got to a token parser, we have to start with a declaration of what kinds of tokens are in there. If you open up the Roslyn source, you'll find something pretty similar too for all of the, it's quite mind-boggling looking at all the tokens that are used to parse Csharp. But in this case, we've got expression token. I tried to keep the names really short so they fit on slides. This is using just simple members for number and duration. When you see those in a message, that's just the name of the token. The example there just makes it possible to say expected L paren rather than the word L paren. Now, taking the input and processing it into a list of tokens is a job for a tokenizer, which you can write by hand if you really want a fast, industrial strength kind of tokenizer. Or if you're using Superpower that we're looking at, you can use a shortcut method called Tokenizer Builder, and that is really just a list of rules that you will apply one by one through the input. And as soon as one of those matches, then produce a particular kind of token and add that to the stream that we're going to parse later on. It really reads top to bottom. And when you see match character equal to plus, that's the same kind of character parser that we were just looking at in the simple text parser example. Again, we've got a little bit of ordering and ambiguity to deal with, and at the end we have span.whitespace to discard all of the stuff that we want to ignore. You'll see duration is tucked in there, and that duration is not from the library of parsers that Superpower provides. It's just the text parser that we wrote that turns durations into time spans. It doesn't matter what kind of output the parser produces to use it in a tokenizer like this. So you can build tokenizers really quickly. Some subtleties. There's a little example in the bottom left corner. Depending on how you want to structure your language, you might not be comfortable with 45D6 being a duration of 45 days and then the number 6. In that instance, if we have a duration or a number, we might want to require that some other tokens appear around them so that they're delimited, and that's what that extra flag that's getting passed through to those rules is. If we go through the parsers that we already have declared and see how they get transformed by this process, the structure stays very much the same. And this is something that it took a long time for me to really realize. The technique, even though you're working on tokens instead of characters, is just the same. You work through and you want to match some particular thing. It's not a character equal to something. Here we go and matched a token of the kind expression token.number. And then we take that value, apply some kind of text parser to it to generate some strongly typed thing, and then we turn that into the node that's going to go into our expression tree. But the transformation is pretty mechanical, and you can really start out with a text parser and move to a token parser, or I can't imagine you'd want to go the other way. But factor is another example that just shows how the structure is very much the same. We're parsing a left paren first. Instead of that being the character, it's the token, and then we go back and recurse over the expression, or we end up trying to parse the literal rule if we don't see a left paren. And the combinator names are all very similar as well for working with tokens or working with characters in Superpower. So it's a little bit of a Swiss Army knife library in that it has facilities that kind of match for both of these things. I ended up writing it mostly because I was doing a lot of character-based parsing, but getting frustrated at not being able to produce error messages that people could understand, and then having to answer questions about why something was broken. Okay, so a little bit of an example now, though, of one of the other benefits of having a tokenizer instead of just writing the parser straight out as a text parser. If we want to put some sort of commenting capability into our particularly throat today, sorry, into this language, so say we want to be able to say 1 plus I have no idea 3, then we can just go and add another ignore rule to this list in the tokenizer, and we can knock that out, those comments out before it even gets down to the parsing stage, and we don't need to go through and examine every rule in that parser we're going to write, where we're dealing with the structure of the grammar, and worry about, say, I want to parse the duration, or I might have to parse the start of a comment. So ordering matters because comments and division begin with the same character. And this is a comment C style. And if we add that one little rule, then we can say 1 plus, and then comment something in there, and we get 4. So token parsing, despite having a little bit more overhead, has a lot of flexibility that gives you a chance to really, you've got a whole extra stage in that process that you can use to deal with these kinds of annoying source processing tasks that otherwise make the parser a lot harder to write. We might have time to have a look at a little bit more of an example. Another thing that, how are we going? Yes, we have 10 minutes to go, just short. 12 minutes. All right. I'm also doing another session upstairs on level 4 after this, which is an AMA. So if we run out of time, I'll be hanging around somewhere up there as well too, later in the afternoon. If you really want to go and crack this solution open and start tinkering with parsers, or if you've got other questions that we don't get time to talk about. But given that we've got a 2-minute budget, let's imagine that we want to start to say, what's the time 7 days ago? The way I would tackle that is we might say now minus 7 days, and just to prove that there's no now in there, I want to show you what it takes to extend this grammar to just do that one more interesting thing. And we'll do it by adding a now token, and we could call it now keyword. Choosing tokens to be more specific rather than generic makes it easier to write a really precise parser. So we add our token there, and the tokenizer will have to produce those tokens when it sees one in the input stream. So we look at the tokenizer, and if we see that span, then we will yield expression token dot now. Yeah. And that should get us to now minus 7 days. We got an unexpected now. We won't worry too much about how to make that message clearer. We expected a duration number. So the problem there is that there's nowhere in our parser that has a rule that will match now. And so we might have to say a duration or number or now. And now is going to be like these parsers that we've got for duration and for number. And it's going to match a token equal to now. No, expression token now. And it's going to have the value new now expression. No, let's call it now value. typing is okay. And they're always going to, it's always going to have the same value because now will always be something that we evaluate, and rather we don't have to have different kinds of nows, so we can just drop a, not Control C. We can drop a node into the expression tree. Doesn't really matter what it does. Oh no, why did I do that? Now, okay, now I can move it. And now if we run the program, hopefully that will work. No. There's no covariance, unfortunately. We have to cast it to an expression for reasons of struct and other things being involved that Csharp won't let us use variance for. So now minus 7 days. Okay, so now we're getting somewhere. So, so once we evaluate that expression, we're going to need another element in our switch statement here. Yeah, and that's going to be, we're going to match a now value, and the result is going to be a new datetime result. And that can just be datetime.now. I would always use UTC, by the way. Okay. Yep. And all right. We have to implement toString just so that we can show this in the output. We'll just say okay. We're getting close. Really? That's my test. Let's just, who needs tests, yeah? Okay, now we've worked our way through, so we can accept now minus 7 days, and we have value 7 days can't be subtracted from right now. Okay, we've got the we take the challenge in the evaluator. We're going to dispatch a subtract. So if the left is a duration result, no, if the left is going to be a datetime result, dt, and right is duration result, we'll say de, then we can take, so if I have a date time and we subtract a duration, we have another date time, and that's going to be the date time value, let's say minus the, okay, and that's going to be de. We better actually add something to that. Create property value. I shouldn't have called it now, should I? Okay. Let's say value was now. And then we can just do value to string. Why did we not get that right? I guess we have to dispatch that. Ooh. Let's see if we get a syntax error. We didn't. So now minus 7 days. I hope you could follow all of that. But just on the fly, I suppose, there's not. This is again. You can just take an existing grammar and bung things in and hack away until it works, and impress all of your colleagues with fun little languages in your programs. So. We talked a bit about text parsers, which we introduced at the start, and we really show how text parsers are just programs that chomp through strings and return results. And we've got combinators to do all sorts of fancy things and make real sophisticated parsers out of those. And then we've got token parsers, which take a bit more machinery, and they're not so quick to write or understand. But I really think if you are going to show this language to an end user, then you should consider taking that approach. And there's tools out there to do that without a whole lot more effort than if you're working with just the plain text. So quick recap. Languages really do rock. I would hate to be living in Access Query Designer all day, and you would too. Parsers are programs. You can all write programs, you can write parsers, and you probably should. You should at least consider where these things could make the software that you build better, because I've hopefully torn away the veil, and there's no magic in there that you're not capable of just getting in there and hacking out with a debugger and unit tests and all the usual tools that you use to write the software that you're already shipping. So I hope that you will give it a shot. Thanks very much for coming along. I think I did want to call out, so we're looking at Superpower. There's another language in Csharp called, that's written in Csharp, another library in Csharp called Sbrocco, which is similar but only deals with text parsers. That was my first attempt. It's still quite widely used, and it's probably also a useful place to find lots of examples if you want to parse different kinds of languages, because there's JSON parsers and XML parsers and all sorts of things written for that. There's a parser out of some folks at Stack Overflow called Pigeon, and Pigeon is a performance-oriented kind of parser combinator library, versus Superpower is much more oriented towards those good end-user error messages. So that might also be worth looking at if you've got a lot of data to process. Sadly, it's not 10 minutes, and so the joke is going to fall on its face. But we might have a few minutes for some questions if anybody has anything they'd like to ask. Michael? Are there limits to what can be parsed with combinators? I'm really not the person to answer that definitively. I think any sane language that you're likely to want to parse yourself can be attacked this way. So even context-sensitive languages where you've got to carry some state down that tree, you might have to do a little bit of acrobatics. But yeah, combinators can definitely be used to attack just about any language that you'd see day to day. Combinators are really just a nicer implementation of recursive descent parsing, which has known sort of capabilities, and it's used for most of the programming languages that we already work with. So chances are pretty good that whatever you're plugging into your IDE is getting parsed with something at least partially using these same techniques. Any other ones that we're going to squeeze in? Okay, thank you very much for coming along. It was lovely to be able to come by.